Hi, I'm Emily Collins, and my research project is evaluating the new normal, how machine learning can be used to evaluate social distancing regulations in public spaces. And I'm partnering with Pulse Software. The ongoing impact of the coronavirus pandemic has directed significant focus on maintaining health and safety through physical and social distancing measures. Social distancing is maintained through reducing the rate of contact with other people and has proven to be effective in preventing the spread of the virus. Social distancing has wide-ranging implications, from travel bans, capacity limits in venues, and new working from home arrangements. This is becoming the new normal, and to ensure these measures are followed, social distancing patterns need to be monitored and evaluated. So how can machine learning be utilized to spatially analyze real-time data to detect social distancing in public spaces? This research project aims to create an AI-based monitoring system utilizing real-time data to identify and evaluate social distancing. Real-time data monitoring can be applied to evaluate how effectively people stay the required 1.5 meters apart in public space, potentially allowing for better management of the distribution of people. The objective of this research is to create a system that can be implemented anywhere to quickly and efficiently detect social distancing within spaces, allowing us to understand and analyze physical distance patterns. For my literature research, I looked at the analysis of pedestrian activity before and during COVID-19 lockdown, using a webcam time-lapse and machine learning. The hourly time-lapse from webcams were used in this study to estimate how pedestrian activity changed during COVID-19 lockdown. In the first stage of the analysis, a state-of-the-art machine learning algorithm is used to detect people. They then split this HD image into smaller tiles, which increased the number of detected pedestrians by over 50%. They found that the number of pedestrians decreased from 33 up to 85% in locations in the town. The presented method allows for more efficient detection and counting of pedestrians from HD time-lapse webcam images, and they compared 4 different machine learning programs. This is my project workflow, with the main sections of the prototype development, including the camera setup for live video data and the script development that analyzes the data. I utilized an IP web camera phone application, where the camera is placed in a fixed location where the approximated distance and depth is defined. This live video is then displayed on a web page developed using JavaScript. TensorFlow, an open source platform for machine learning, is used to build and train the application to detect people through utilizing machine learning. JavaScript is then used to find the center points of people detected and calculate the distance between them. This live data then be analyzed to assist in decision making in the future. The first step is camera setup, real-time data taken from an IP webcam. The steps for this include downloading the IP webcam app on a smartphone, setting the camera at a fixed location, opening the app and copying the IP address. Anyone can download the app, it can be used anywhere and can be monitored on any computer. Next is the script development, where we apply object detection to detect all people in a video stream, compute the pairwise distances between all detected people, and then based on these distances, check to see if any of the 2 people are less than n pixels apart. First is the video output. This is where we copy the IP address from the IP webcam and put it into our website. The script takes the IP address and displays video output as seen here. This was done using JavaScript. Next is machine learning and object detection. I used TensorFlow for this after analyzing and testing a few different platforms. I found that this was the most accurate. To do this, I had to download the TensorFlow library. Next was creating bounding boxes and center points. By creating a canvas for the video frame, I was able to use TensorFlow to detect what was in the frame and then draw a box around the people and objects. I can now use the center points to find the distance. The center point was found by measuring halfway in and then halfway down the box. Setting the camera at a set location, I found that 1.5 meters was 200 pixels. To measure the distance between center points of people, I used a Euclidean distance formula, sending an alert if people were closer than 200 pixels by making their bounding boxes red. You can see here that it took some calibration to get the bounding boxes in the right spots. Next is measuring the distance. If the distance is greater than 1.5 meters or greater than 200 pixels, it will render green. If the distance is less than 1.5 meters or 200 pixels, it will render red. To test this, I used some still images that I found online and shot them with my IP webcam. You can see here in the left image that people are closer than 200 pixels, and in the right, they're greater than 200 pixels. After initial testing, I found that there was an issue with the depth factor. So as the detector uses pixels to define distance between people, there is currently no depth factor. We found that this could be estimated based on the Y value of an object. The higher the Y value of the object, the closer they are to the camera. This was not completely accurate, but it was more accurate than our previous method. So then I continued to do more testing. After evaluating and testing my prototype, I found that for more accurate results, I should look into calibrating the camera through intrinsic and extrinsic parameters so that I can map pixels to measurable units. As I rely strictly on pixel distances, it won't be as accurate. The first step to doing this is to utilize proper camera collaboration. This will yield better results and enable me to compute measurable units rather than pixels. Secondly, I would like to consider applying a top-down transformation of the viewing angle. From here, I can apply the distance calculations to the top-down view, leading to a better distance approximation. I could also look into implementing depth sensors. This tool has the capacity to be developed on a larger scale, with cameras being set up on drones to monitor and analyze beaches, parklands, railways. This would not only tap into stopping the spread of disease, but evaluate how spaces are used, if they are being used effectively and efficiently, and how they could be reimagined or redesigned to better accommodate people. Future planning could include privacy protection, depth censoring, counting the number of people in a space and how many are social distancing and how many are not, and what else we could use machine learning for that could be beneficial for spatial and pedestrian analysis. Things that could be included in this could include whether the person is wearing a mask or not. Social distancing can be detected using machine learning and spatial analysis. And in order to do this more effectively and on a larger scale, pixel mapping and camera collaboration needs to be implemented. The physical distancing tool assists with making COVID and post-COVID life simple, showing how movement patterns in public spaces correlate with social distancing standards. Thank you.